Welcome back to Lesson 3 of our GD&T Master Course. I am so incredibly excited to have you here today. In our previous lessons, we laid down some of the basic terminology, but today we are going to explore a foundational concept that will completely shift how you think about engineering drawings. We're going to uncover exactly why size alone just isn't enough to control form, and how ASME rule number 1, also known as the envelope principle, solves one of the most critical, headache-inducing manufacturing problems out there.
Okay, let's jump right into this with a scenario that literally plays out on shop floors around the world every single day. Picture this. You're measuring a newly machined pin or a shaft. You grab your calipers, you check the diameter across a few different points, and it perfectly meets your size tolerances. You think, great, it's a good part, right? But then, you take that exact same pin, walk over to the assembly line, try to insert it into its mating hole, and boom, it jams. It completely fails to assemble. So why does that happen? Well, it's because the pin, while technically correct in diameter, is slightly bent, kind of like a banana. This is the exact moment where size alone fails us, and where the rules of GD&T step in to save the day.
To fix this incredibly common issue, here's our quick agenda for today's explainer. We'll cover why GD&T rules matter, features of size and MMC, rule number 1, inspection and applications, and finally, how to avoid common mistakes.
Kicking things off with Section 1, Why GD&T Rules Matter.
You know, in the past, there was a real chaotic kind of fly-by-the-seat-of-your-pants mentality when it came to engineering drawings. A designer would sketch something up, hand it over to manufacturing, and just assume they knew what was meant. But as we all know, assumptions lead straight to the scrap bin. The ASME Y14.5 standard removes all of that guesswork. It creates a highly structured approach. We absolutely need these rules so that a drawing means the exact same thing to the designer who drew it, the machinist who cuts it, and the quality inspector who measures it. By establishing these consistent rules, we ensure clear communication of the design intent, which naturally leads to predictable manufacturing and reliable, repeatable inspection.
Moving right along to Section 2, Features of Size and MMC.
First up, we need to talk about the feature of size. This is a term you are going to hear constantly in GD&T. By definition, a feature of size must be a cylindrical surface, a spherical surface, or two opposed parallel elements or surfaces that can be directly associated with a size dimension. So whether it's an external feature, like our problematic shaft from earlier, or an internal feature, like a slot or a hole, it literally must have those opposed parallel elements to be considered a true feature of size. If it's just a random flat surface floating in space, it is not a feature of size. It needs measurable, opposable size limits.
Now here's where things get really interesting. Maximum material condition, or MMC. This is such a critical modifier. MMC is the condition where a feature of size contains the maximum amount of material while still remaining within its stated tolerance limits. You can think of MMC as the heaviest a part can possibly be while still passing inspection. For an external feature, like a shaft, MMC means it's machined to its largest allowable diameter. But for an internal feature, like a hole, MMC actually means it is drilled to its smallest allowable diameter. Why? Because a smaller hole means more metal is left on the physical part itself.
So let's look at the calculation steps to actually find this boundary. We call this the virtual condition, and it represents the absolute worst-case scenario for your mating parts. If you have an internal feature, like a hole, you take its MMC size, remember, that's the smallest the hole can be, and you subtract any geometric tolerance, like a position tolerance. But if you have an external feature, like a shaft, you take its MMC size, the largest it can be, and you add the geometric tolerance. This simple math creates an imaginary physical boundary that guarantees if your parts respect this envelope, they are going to assemble perfectly every single time. No hammers required.
All right, let's get into Section 3, Rule number 1, the envelope principle.
If you remember one single thing from this entire lesson, please commit this definition to memory. Rule number 1 dictates that a size dimension inherently controls both size and form. What this means is the feature must have perfect form at its maximum material condition. In practical, everyday terms, the envelope principle dictates that if a shaft is machined to its absolute maximum allowable size, it has literally zero room to be bent. It must be perfectly straight and perfectly cylindrical to fit inside its imaginary boundary. Now, if the shaft is machined slightly smaller than MMC, it's actually allowed to bend slightly, but only as long as it never violates that strict outer virtual envelope.
Take a look at this drafting example on screen. The size tolerance automatically creates a virtual boundary, an envelope, that the physical part simply cannot violate. This directly links the allowable form error, things like straightness or circularity, to the actual local size of the part. If you produce a part at the absolute maximum limit of size, the form error has to be 0. As the local size shrinks into parts from MMC, you actually get a bonus tolerance for form error. It is just an incredibly elegant way to ensure parts always fit together without needing separate redundant callouts cluttering up your blueprint.
Now hold on a second, because there is a massive global distinction we have to make right here. It is absolutely crucial to know which standard your manufacturing shop is actually using. Under the ASME standard, which is widely used in North America, this envelope principle is totally automatic. Rule number 1 applies by default. But if you're working with the ISO standard, which is common in Europe and globally, the size tolerance only controls the 2-point local size. It does not automatically apply this envelope boundary. This means under ISO, you could technically receive a perfectly measured, yet totally bent and completely unusable pin unless you explicitly ask for the envelope requirement by using a special symbol right on the drawing.
Let's take this down to the shop floor. In Section 4, Inspection and Applications. We all love our calipers and micrometers, right? They're fantastic, everyday tools for checking the local 2-point size of a feature. But as we established at the very beginning of this explainer, 2-point measurements are completely blind to the overall form of the part. A micrometer can tell you that the diameter is perfectly correct at one specific cross-section, but it will miss a bent shaft entirely. This is exactly why just taking a few micrometer readings is never enough to guarantee a part actually conforms to rule number 1. So how do we verify that a part actually respects the rule number 1 envelope? Well, inspectors rely heavily on functional go-no-go gauges, like the functional gauge shown here, checking an internal boundary. A go gauge physically replicates the absolute worst-case mating condition, that virtual condition we did the math for earlier. If the part can smoothly slide into the go gauge, it completely proves that neither the size nor the form error has violated the maximum allowable envelope. It's a remarkably quick, physical pass-fail test that perfectly aligns with the real-world functional requirements of the assembly. Of course, we don't always have the luxury of physical gauges sitting around. For highly precise automotive engine shafts or aerospace bearing fits where physical gauges are either totally impractical or way too expensive to manufacture, quality engineers step up to coordinate measuring machines, or CMMs. As the probe digitally maps hundreds or even thousands of points across the surface of the precision-machined part, the software calculates whether the entirety of that mapped surface sits cleanly inside the theoretical tolerance envelope defined by rule number 1.
Almost done. Section 5. Avoiding common mistakes.
Nothing drives up manufacturing costs and infuriates your machinists faster than falling into a few very specific traps. First up, overcomplicating designs. You should only apply super tight tolerances where they are absolutely crucial to the fit or function of the assembly. Playing it safe by just tightening everything across the board just makes the part wildly expensive. Second, confusing your material condition modifiers. Mixing up maximum material condition with least material condition causes perfectly functional parts to get rejected right there on the floor. And third, failing to define the shape and size of the tolerance zone clearly. This leaves your manufacturer guessing, and guessing always leads to errors.
Instead of scattering arbitrary disconnected callouts all over the page, look at how Professional Blueprint handles this. It uses distinct feature control frames and clearly defined datums. This gives the manufacturer exactly the limits they need to hit, no more, no less. Notice how clean the hierarchy is here. The drawing doesn't overconstrain the process, it simply defines the boundaries of acceptable variation. This clear syntax ensures everyone, from design to inspection, is reading the exact same language.
I absolutely love this quote I found from a veteran engineer on an engineering forum. It says, "You should apply GD&T when you think a more accurate description of the problem will yield a cheaper part and a happier manufacturer." We don't use GD&T just to make our drawings look fancy or because we're working in aerospace and feel like we're obligated to. We use it specifically to maximize tolerance zones, prevent functional failures like those bent shafts, yield much cheaper parts, and foster a happier, vastly more efficient manufacturing team.
So, let's wrap this up. What is the bottom line here? First, size alone does not guarantee your parts will actually assemble. A part can measure perfectly but still fail if it's bent. Second, ASME rule number 1 bridges this exact gap by mandating perfect form at maximum material condition. Third, combining size and geometric tolerance creates a virtual condition, a strict envelope boundary that your part absolutely cannot violate. And finally, applying these rules clearly and correctly drastically reduces scrap, lowers your costs, and keeps your production running smoothly. Rule number 1 really is your ultimate safeguard for functional assemblies.
With these foundational rules fully covered, you are completely ready for the next step. But before we go, ask yourself, how many parts out there in your current assembly line are technically in spec, but fundamentally broken because someone forgot about the envelope boundary? Next time, we're going to dive deep into exactly how we lock these parts into space for measurement. Next lesson, datums, datum features, and datum simulators.